Okay, hello everyone. My name is Jack. I'm a Apache Iceberg PMC member, and I will be hosting this session for everyone here. Here we have Rushil, who is a senior software engineer from Bloomberg, and he's going to talk about building Bloomberg's first incremental alternative data product. And before we start with our talk, I'd like to remind everyone for a few housekeeping items. If you haven't done so already, I encourage you to download the conference app and read the session so that we can build an even better conference next year. Please remember to silence your cell phones and keep distractions to a minimum as we are recording these talks. And on that note, please save all the questions to the end. Please start.
Thank you, Jack. So hello and welcome, everyone. Thank you for joining today's session. As Jack mentioned, my name is Rushil. I'm a senior software engineer at Bloomberg. And in today's talk, I'm going to be walking through our journey of what it took to build Bloomberg's first incremental alternative data product using Apache Iceberg. So the agenda for today's session is we're going to start with an intro on what is alternative data and cover some unique challenges it presents. I'm also going to walk you through our specific use case and some of the obstacles we faced. Next, we'll dive into some key Iceberg features that attracted us to the technology and just some unique characteristics about our implementation and also just some lessons learned. And finally, we'll cover the revision tracking model that we were able to build using Iceberg and how that enabled incremental delivery to our clients. So what is alternative data? And I have this little blurb here, but alternative data refers to information gathered from non-traditional sources. And this can be stuff like social media posts, satellite imagery, credit and debit card transaction data, web traffic, and many other types of sources, which is used by investors and analysts to gain insights about a company, market, or industry beyond what is available in these traditional financial reports. And I realize that may be a little bit of a mouthful, so let me just show you an example. So in this example, you have this graph where you have this orange line, which is tracking the stock price for the company McDonald's. And then you have this blue line, which is based on analytics from de-identified credit and debit transaction data used to track McDonald's sales. And upon first glance, you may already see a pretty interesting correlation between the two. And I think that's an inherent value of the signal that alternative data can give you to be an accurate predictor for stock price. And just want to drill down on some interesting events here. You can see that over the summer of last year, when McDonald's kicked off their $5 meal deal, this was a really interesting business strategy, and a lot of investors and analysts were very curious on how this strategy would actually play out. And what's interesting is you can see shortly after that, the alternative data signal is showing a sharp increase in the trends that we're seeing in observed sales at McDonald's, giving people an early indication that this strategy is likely leading to more sales before the company is actually releasing their quarterly earnings. On the other hand, a negative example, I guess you can say, is towards the end of last year when the E. coli outbreak happened. And when this happened, a lot of people were very nervous about how the outbreak would affect the fast food industry and like specific companies within the sector. And as you can see that it did affect McDonald's fairly significantly, and the alternative data shows that shortly after this outbreak, the trends in observed sales decreased significantly. So again, just these types of insights really allow investors and analysts to be able to understand how a company may be performing and anticipate stock price movements as an early indicator before those quarterly earnings reports come out. So really neat and really powerful. And while alternative data is really neat and powerful, there's also some unique challenges and characteristics about it. So these data sets are massive, and they're often in the terabyte scale range. The data is quite messy, as I'll show you in the next slide, and it takes a lot to actually clean and correct and actually make this usable for analytics. It is quite common in alternative data to have late arriving data. And one major challenge in alternative data is handling historical restatements. And historical restatements are just the norm in alt data, and this is where providers revise past records to account for new information or to correct errors. And this concept is going to be fundamental to our talk today. And I want to just show that processing alternative data, it's not a simple ingestion or it's not a simple ETL workflow. It truly takes a village to actually turn this data when we first see it into a usable product. So after we ingest, we have to standardize and clean the data. We have many layers of enrichment and corrections that we have to apply on top of that. We then have a lot of modeling that we do to generate forecast, and then we aggregate the data till we ultimately publish that data for consumption. And below, we have just a very simplified example of what credit and debit card transaction data may look like when we first see it. So what you can see here is you have a record per each transaction. You have a transaction ID. You have a member ID, and this member ID is de-identified and scrubbed with very strict PII requirements. We have a description string of the transaction. We have a location value, or in this case, it's just simplified to a city. We have some timestamp of the record. In this case, it's a date, and then we have the amount of the transaction. So here, I just want to show one example of this is the value we received for city. And you can probably tell that there's no such city called hulu.com/bill. So this is a case where we would actually have to correct this value and really figure out where this transaction actually took place. And building off of that, you have this example where we did not get the value at all. So in this case, we have to impute or derive where this transaction for Uber actually took place. And lastly, you have this description string, and many of you may be able to attest to this on your credit card statements, is these description strings are indicative of where you shopped, but they're not always in the cleanest, most parsable format to actually understand what happened. So we have to maintain fairly robust logic to actually parse this and tag this transaction to a specific brand. And in this case, we would probably tag this to the brand of Starbucks. So now that we covered just a little bit about what alternative data is and some aspects about what it looks like, let's zoom in on our specific problem statement that our group faced. And before I do that, I want to just give you an overview of what our data platform looked like. And our data platform, unlike a typical data lake or a lakehouse, is more narrow scoped, and it's really focused on enabling the reliable processing, publication, and consumption of data. It provides a streamlined workflow or a paved path for our data scientists and our engineers to build data products without worrying about the underlying complexities about stuff like dependency management and how to wire up your dependencies for your job, worrying about orchestration of your big data jobs, and also just having to worry about the data lifecycle management. It's really meant to abstract a lot of this stuff away so our scientists and engineers can really just focus on producing this data product. Our data platform is run on Kubernetes. We use Spark for our compute and processing layer, and we also use Parquet, Trino, and S3 for our storage and query layer as well. And since our platform was based around Parquet, and Parquet being an immutable file format, it really encouraged a full data load philosophy. And with the goal to provide simplicity to our users, along with understanding the characteristics about alternative data, such as late arriving data or constant restatements from our data provider, we had our data processing jobs really based around reading the latest full input and then producing a brand new and distinct output. And this fared fairly well because this was an easy developer experience. Our engineers really just had to think about, when I have this complete and full input, what do I need to do in my Spark job to transform that to produce my output? They did not have to really think about these concerns about late arriving data or if the entire input was backfilled. It was just given to them in the complete and the newest state. And additionally with this, safety and item potency was also baked into this workflow. So because each job would produce a new and distinct output, a rollback would be as simple as just repointing your product to a previous output location. And lastly, writing the entirely new output was acceptable, I would say, for our aggregated data products because these deliverables were not very large in size. But I think this sets the stage for the problem statement that we were presented with, and that was to build and deliver a daily non-aggregated data product. And compared to our aggregated products, this non-aggregated product was much larger. It was around 7 terabytes of compressed Parquet files in total. And because our platform only supported entire output rewrites, we couldn't really apply and track the revisions across the history of a table when we would produce these restatements, or we would essentially reproduce the entire output. And because we would reproduce the entire output, in fact, every record in that table would be considered new, and it would have no knowledge of the past. And really the only way we could build and deliver this product with the platform we had would be to essentially ship the full data set of 7 terabytes every single day. And this was a showstopper. This was just way too much data for our clients to ingest daily and wouldn't really make for a desirable product that we could actually sell to our clients. Especially considering that on a daily basis, most of the time, only a small set of that data is actually new or it's being updated. And ultimately, what we really needed is we needed a better way to track and deliver just the necessary updates on a daily basis. And with that problem statement in mind, I want to just highlight some key features that attracted us to Iceberg and what gave us the confidence to invest in it as part of our data platform. So one of the key reasons we chose Iceberg was the right reliability. With Iceberg, you have safeties in the way you can insert, update, or delete data without any table corruption. And unlike our previous system, we're not required to reprocess and rewrite the entire output, especially only if a small portion of that table changes. We can safely just evolve that existing table and efficiently write only the new data or the revised data. And one thing that I mentioned before is our platform gave us a lot of safeties, and idempotency was one of those. And with idempotency, it essentially means that if your job is rerun again, you want to make sure it's not going to have any side effects. So you want to make sure it's not like duplicating the data that's being inserted or corrupting your data in a way you don't intend. And with Iceberg, what we found is we're still able to achieve idempotency using the merge statement. And this brings us to another major advantage, which is snapshot management. So snapshots in Iceberg provide independent point-in-time versions of the data set. And this is really critical because it provides a lot of safety, and it gives you the ability to roll back to a previous state or a previous version in case there's any mistake or data corruption or bug that was introduced. So this is a really important thing for us because we build and we ultimately sell these data products. So in case there's some issues in the data, we need a quick recovery. And lastly, one of the most powerful features of Iceberg is their time travel queries. So with time travel, what you can basically do is you can, of course, query the table against its latest state, but you can also query the table at any given point in time. So in this simple example, what you see is if you're to query the table as of what it looked like today, for ID equals 1, you would get the value of San Francisco. But you can also view what that record looked like at a certain point of time. So if you add this as of timestamp qualifier, and we want to see what the table looked like on January 1st of 2024, we can see that the value it yielded was San Jose. And this is extremely powerful for us because, again, as a group that builds and sells these data products, we need the ability to debug, audit, and verify these changes over time. And this is not just important for engineering teams, but also our customer support teams that need to respond easily and quickly to any type of client inquiries that come in of specifics about what the data is and why the data is a certain way. So with the decision and with some of the key features of Iceberg, we had a lot of conviction that Iceberg would be the right choice for the next evolution of our data platform. But I want to kind of go over some unique architectural decisions that we made when we implemented Iceberg, and also just some lessons we learned along the way. And as Ryan mentioned earlier today, the catalog is the famous thing in Iceberg, and it's the ultimate source of truth that tracks the Iceberg tables and their Iceberg-specific metadata. And there are many different implementation options when it comes to choosing how to implement the catalog, and it really brings up the question of how do you choose. And what we looked at when we had first started this journey, and given we had started this journey over a year ago where there were no REST catalog, open source REST catalog implementations available, so we looked at some of the easier options that could get us up and running. The first thing we looked at was Hive and the Hive Metastore, and this was probably the easiest for us to actually utilize because we were already using the Hive Metastore in our platform. But as maybe some of you guys can attest to, we were already facing some scale and performance challenges with the Metastore. So this was a pretty quick decision to not add more load there. Another solution we looked at was AWS Glue. So our platform runs in AWS, and always making use of a managed service is nice because it gets you up and running quickly and easily without having to worry about any maintenance burden. However, we did not want to be locked in to just a AWS opinionated solution, especially because Bloomberg has a fairly large presence on-prem. And additionally, as we were thinking about how we would scale and iterate on this platform, we really felt that the access control would be a little bit just more limited here with having to use AWS primitives. And also multi-tenancy would be a little bit harder to scale as well. And lastly, another solution we looked at was JDBC. And JDBC is simple, it's easy and familiar to stand up and connect to a database. So this was definitely nice. But similar to AWS Glue, we also noted that access control is, again, limited through AWS or database primitives, and also it would just be a little bit harder to scale when we're thinking about a multi-tenancy platform. So ultimately, we decided to use the REST catalog, and it seems like when we had first started this, there are a lot more open questions, but now it seems like more people are deciding to leverage the REST catalog. And that makes a lot of sense, because for us, what we found at the time is it was able to support not just our short-term goals, but also our long-term goals as well. So our catalog implements much of the open API spec, and we also have some custom endpoints as well used by our platform internals. One of the things that we found that we really enjoyed with the REST catalog is it gave a lot of flexible integration with different query engines. So our platform uses Spark, Trino, and Python, but we also did not want to be super opinionated, as there's other query engines that people are always looking to use, and we wanted to make sure we had a ton of flexibility there. Our catalog is backed by a Postgres database, and ultimately, we felt that this solution would give us the most flexibility when we're kind of thinking about access control and when we're going to add more tenants to our platform as well. So at the time of this journey, as I mentioned, there were no open source implementations that we can use, so we had to build it ourselves. And we decided to write this catalog in Python because this was a language that our team was familiar with. And we decided to utilize the PyIceberg library for actually interacting with Iceberg. And this was nice because we did not have to rewrite or maintain much of the core logic. For example, to interact with the database or to interact with the S3 object store or the metadata files. We were able to relegate most of that work to the PyIceberg library and let that do the heavy lifting. So as you can see in this screenshot, this is an example of the list namespaces endpoint. And it really is this simple. We're really just wrapping the service code around PyIceberg and letting the library do much of the work. And some lessons that we learned were when we at first kind of decided we wanted to use the REST catalog, it was a little daunting for us because we thought we had to just build it completely from scratch. But the decision to use it, to write it in Python and use PyIceberg made it much easier, and it allowed us to build it much quickly in a stack that we're familiar with. The decision to also use the REST catalog just gave us a lot of flexibility of conversations we were having of how we wanted to share that data beyond the confines of just our internal platform environment. However, I will say, by using PyIceberg, we were limited by the features of the library. So I think at the time when we were working on this, the latest version of PyIceberg was like 0.4.0 or 0.5.0. We contributed back to the library, so we added certain features, we fixed certain bugs, but there's still gaps in those versions. So for example, at the time, our catalog could not support any maintenance operations just because PyIceberg could not support that. And I think a lesson learned in kind of looking at what the landscape of Iceberg looks like today, certainly things have come a long way. You now have these open source implementations available, so that is something we are considering in our next iteration of the platform, of considering to make use of one of the more open source ones like Unity or Polaris, or at least considering writing it in Java, where we can make use of the Java API, which is at least a more complete implementation. Another characteristic of our architecture that I want to talk about is how we manage data visibility. And some design goals that we had here is we wanted different tenants of the platform to view different subsets of the namespaces and tables within the catalog. We also wanted to handle this in a simple way without duplicating data across multiple locations. And this especially was the case when we were thinking about environments. For example, if you are familiar with the concept of a development environment and a production environment, these are kind of good separations when it comes to like rolling out software, but when it comes to actually exposing data, we wanted a little bit more flexibility there. We wanted our users to be able to like run in a development environment and also query against production data to help their efforts. And we wanted to do this without duplicating that data by like, redundantly copying the same table that's living in production just to like a separate bucket, just to fulfill the needs and get that access in dev. So we wanted to be a little creative here. And also, because our platform is really, at the time, only intended for internal tenants, we did not require a sophisticated authn or authz level framework. We already actually maintain fairly tight controls of the data that a user can read. We require a user that writes a data job to explicitly declare the inputs, and those are the only inputs that they will have access to. So we wanted, again, like not to have such a heavyweight solution to accomplish this. And if you remember, one of the implementations of our REST catalog was we used the Postgres database as the backend. So we leaned into a Postgres native feature called row-level security. And if you're not familiar, what row-level security is it's essentially a security feature that allows admins to define policies that control specific rows of data that can be accessed by user roles. And in this picture, what you can see is if you were to create a policy where individuals can only view their own data or their own to-dos in this sample table, even if you were to go in and you were trying to do a select star from the table, this policy would take into place and it would effectively add a filter and effectively filter that data as if like you can only view the data as if the column is matching with your user ID. So again, this just gives a layer of safety and a layer of restriction. So based on these policies, you have like a different experience when you're actually querying the data in the table. And what we did is we used row-level security policies, and we created policies based on Iceberg namespace properties. And in case you're not familiar, each Iceberg table is organized into a logical grouping called a Iceberg namespace. And these namespaces have these key value properties attached to it. And this is really nice because it's native to the Iceberg spec. So this can be dynamically managed over the lifecycle of the Iceberg namespace and the Iceberg table. And for our system, we specifically actually only handle this when the table is first created. But it is really nice that we can evolve this at any point in time. And what this kind of looks like, an example here is in your catalog, you have two main tables. You have your Iceberg namespaces table, which will look something like this. And here you can see we have two namespaces. We have namespace A and namespace B. And namespace A, we have tagged it with two attributes or two properties. So you have an environment equals prod and a medallion equals gold. And then for namespace B, we have a attribute for environment equals dev. And similarly, the Iceberg tables table, which is the important tracker, which tracks your actual Iceberg table with its metadata path, you'll also see the namespace is part of this table as well. So let's just go through an example of like what this could look like. So let's say our first tenant is an admin, and our admin does not have any restrictive row-level security policy set. Therefore, the admin should be able to view and interact with all the data. So when they try to list the tables, they're going to see the two namespaces and the two tables that live in this catalog. Cool, simple enough. Now our second tenant is the dev tester, and the dev tester has a policy to only view namespaces with the attribute environment equals dev. So when they go to list the tables against the same catalog, they're only going to get one table returned back. And that's because only namespace B it has the attribute of environment equals dev. And now we have a third tenant, and let's say this third tenant is some type of researcher, and they have a policy to only view namespaces with the attribute medallion equals gold, maybe signifying some type of cleaned or curated or complete analyzable data set. So when they go to list the tables, they're going to get only namespace A to be returned and table A to be returned. So here we can just see an example of within a single catalog and a single database, these three different tenants have a pretty different experience when it comes to actually data visibility within the ecosystem. So what did we learn here? The approach of row-level security is data-driven. So further data visibility changes is either handled by database migrations for policies and users, or updating namespace properties via an engine connecting to the catalog. It solved one of our initial goals where we did not have to duplicate or sync data across different environments. And data visibility is blocked at the database level, though this is coupled to a Postgres backend. So this is a feature native to Postgres, so it would be a little bit harder for us to evolve this and iterate on this if we were to ever swap out that backend. And overall, I would say that this solved our problem very quickly and easily without needing to implement a sophisticated access control framework. But in our next iteration of the platform, we are looking to revisit this and looking to actually add a more proper access control framework for this. So now that I covered some Iceberg implementation details, let's shift focus to a key product-oriented benefit that we got by using Iceberg. And that was how we built our revision tracking model. The overall impact for this work is the revision tracking model allowed us to identify and extract revisions. It also provided a deeper insight into these data revisions, really allowed us to ensure a high level of data quality. And lastly, it enabled us to build an incremental daily revision delivery system, resulting in a minimal amount of data our clients had to ingest on a daily basis. And just to recap, prior to Iceberg, we had one way to produce a data product where we had a complete full input and a Spark job that would take that and produce a brand new and complete output. But with Iceberg, we had a newer paradigm here. So we had our full and complete input, but we also had the existing Iceberg table. And what we could do is we could take both of these and figure out how we want to evolve this existing output to our desired state. And this is all just a fancy way of saying that we can upsert records into our table over time. And what this actually fundamentally allowed us to do is it allowed us to utilize new data modeling techniques, which we couldn't do before. A particular data modeling technique that we used was slowly changing dimensions. And this is essentially a framework for updating and maintaining data over time as they change. And there are a couple different variations of slowly changing dimensions. We chose type 1, and type 1 is essentially when a record in the table changes, the existing record is updated or overwritten. And this solved the problem that we had at hand without increasing the size of the table significantly, like some other data models do, like slowly changing dimensions type 2, for example. And what this looks like in practice is, let's say we have this table, and this is its initial state, and it's modeled using slowly changing dimensions type 1. If we run an upsert, meaning we want to update an existing record, and we want to update record number 2 and change the city from Miami to Austin, all you do is you simply just overwrite that value that you can see in this after picture where the new value of city is Austin. Simple. And then also, because we're constantly receiving new data, if you need to insert new records that you haven't seen before, all you do is insert it. And taking this a step further, when we handle the upsert logic to update an existing record or insert a new record, we can also manage columns that track the timestamp of these operations. So what we can see in this example merge statement is, we have our typical clause to see like when something has been matched and when we make a decision to update a record or update a value. So whenever we update maybe the target value to be equivalent to our new source or a new input, we're always going to change this updated timestamp to be a monotonically increasing timestamp. In this very simple case, it could be equivalent to the timestamp when this job was run. And additionally, we do the same thing for when we insert data. So when we first see data first insert these records for the first time into this table, we're also going to manage the created timestamp and the updated timestamp to be equivalent to the run timestamp of the job. And fundamentally, what this allows us to do is it allows us to detect what changes, but also when it has changed. And this is going to be really fundamental for actually how we can extract these revisions. And lastly, as I mentioned earlier, safety is really important for us. So we always, in our data pipelines, use the merge statement to ensure we have an idempotent upsert. And once we were able to build this revision tracking model, we were able to understand these revision patterns in a light in which we couldn't do before. And we're able to ask and pose some of these key questions and also answer some of these questions, such as which columns are revisable versus immutable? How often are these revisions happening? As you can see in this graph on the right, this shows the revision volume for one of our tables. And you can see that on a daily basis, it tends to be fairly small and kind of fairly consistent, but it has sharp spikes every 7 days. And this is totally okay. This is actually due to one of our internal methodologies in which we run a weekly backfill. And we had kind of known that this was going to be the case, but we were actually never able to quantify the degree of these revisions till we had this model. We were also able to ask questions such as, are any revisions violating intended functionality? Are things changing in a way that we don't expect? Are there any bugs here that are leaking in? And also, we can understand what is the magnitude of these changes. Are things changing super significantly? Are things changing ever so slightly? Like, what is actually going on at a deeper level? So just to show what this looks like, we really leaned into Iceberg and time travel capabilities here. So this is a really neat example of how we can view our table in its current form and also join it with itself from a previous timestamp. So what we're really trying to do here is compare the before and after picture of this table for a very specific column. So in this simplified example, we're really trying to drill down and see how the revisions are changing in the city column. And what you have here is you have an example that, hey, for this record, it was previously tagged to the city of New York as of January 1st. But now, as of today, the current city is Austin. And this is totally acceptable because as one of the things I mentioned is we're constantly trying to correct our data and revise our data because we have new predictors or new accurate information. So we want to make sure we always have the most accurate and correct data. So this is a totally acceptable practice. However, this case may or may not be. This may be a case where we've removed the tagged value and we now have a blank value. So again, it really just allows us to really drill down and see how these revisions actually look like at a fine-grained level, and it really allows us to uncover what is going on. And some of the outcomes for this is we're able to identify bugs in the system where unintentional revisions were slipping in, like the prior example I just showed, and it really allowed us to improve our data quality in this product. We also noticed that certain floating point numbers with high levels of precision were changing ever so slightly. And a lot of these were actually changing insignificantly for what our product was intending to capture. So what we were able to use is floating point quantization to really ensure we're eliminating a lot of those insignificant revisions, and we're ensuring that all of the changes that were happening are truly significant for our product. And lastly, by understanding what columns are immutable and what columns are highly revisable, we were able to normalize our data model further to keep the columns that had a high level of revisions to separate dimension tables, overall minimizing the daily revision volume across our product. And just putting this all together, at the end of the day, we needed to design a product that could deliver these minimal set of revisions on a daily basis instead of a full table. So what this visual shows is on day one, if this is the state of the table, and let's say we've inserted these two records, you'll notice that the created date and the updated date matches the timestamp when it was first inserted, and in this case, it's just January 1st. So if we wanted to extract the revisions for this date, it would be a simple query from this table where the updated date equals January 1st, and you have your two records. Great. Now on day two, we have run an upsert. So we have changed the second record's value from what it was previously, and then we've also inserted a new record. And what you'll see here is both of these records have an updated date of January 2nd. So when we want to deliver the revisions on this date, we only have to deliver these two records because these are the only two new records on January 2nd. And This is pretty powerful because, as I mentioned before, is prior to this, we had to deliver the full table every single day. But as you can see here, we don't need to deliver this first record because nothing has changed from when we first delivered it in the day prior. And with those foundations, we were able to build an incremental delivery system for our clients. So the very first time a client actually ingests this product, they have to ingest the full table snapshots. And this is around 7 terabytes. But every day after that, they just have to ingest minimal daily revisions, anywhere from 5 to 10 gigs. So you can just see how dramatic of a scale difference this is. And just to summarize the impact of this, if we were to have done this project before Iceberg, we would have full daily restatements of around 7 terabytes every day. And this would lead to a high ingestion overhead and just overall slow processing and costly storage. And lastly, from a provider perspective, this would just be harder for us to diagnose and debug data quality. After Iceberg, we were able to deliver daily revisions incrementally, and this would be anywhere from 5 to 10 gigs, which was less than 1% of the total table. So very significant here. And overall led to streamlined ingestion and processing and efficiency gains in storage and compute. And as a provider, much easier for us to diagnose and debug data quality. So overall, both us and our clients are very happy. And lastly, just to recap a little bit about what we talked about here today is Iceberg provided some really helpful features for us to safely produce and maintain the lifecycle for alternative data products. The decision to implement the REST catalog really gave us a lot of flexibility for accessing and sharing various presentations of the data. And lastly, Iceberg enabled us to utilize different data modeling techniques, which we couldn't do before, to track and ship revisions across large data sets. All of this leading to an efficient incremental daily delivery for a large data product and an overall very successful product offering to our clients. And with that, that concludes my presentation, and I think we have some time for questions.
Yeah, for anyone has a question, please raise your hand and you can pick, and I will give you the mic.
Could you expand with an example of how you ran into limitations with the access control just using the AWS primitives?
Yeah, so we never pursued it, but it was really because like if you were to use a solution like Glue, for example, the access control would be like mainly through like IAM and using like IAM. But with REST at least, like you have a lot more flexibility of how you want to govern that access with perhaps some type of like token mechanism or something like that. So we just wanted a lot of flexibility. Like you can always use IAM, but especially because we have a fairly large on-prem presence as well, we didn't want to like have that be like the opinionated path to like get access to the catalog.
Hi. My question is, you used a combination of create and update dates as well as snapshots in order to find differences. Why did you need to use both? Why couldn't you just rely on snapshots?
Yeah, no, that's a really good question. We wanted this to be native to our data model. So like snapshots and doing the diff between snapshots is a valid way of doing it. And now I think like they have like the whole like the CDC view that makes it really easy. But one of the nice things is like we're able to get more analytics out of just having it native to our data model because it's much easier to just run that native SQL query to do like some of the things that I showed to like drill down and see like on a specific date if you're to compare like two random dates, like what things are like looking like. It's just we found it to be a little bit easier to have it native to the data model. But it is totally valid. You don't need to have it in the data model. You can use the snapshot lineage mechanism.
Okay, great presentation, Rushil. I'm trying to map your initial use case, which had that wrong state code or state or location,
Yeah.
and bring this back to the example. The way I understood this is you have made your data observable. You are able to now find the needle in the haystack, that how did this data change? And then instead of looking at the full fidelity of the data, your teams are able to identify these type of issues. Was that correct? Like, I'm trying to map all of this back to the issue you stated in the beginning.
Yeah, so are you referring to like how we correct data, or?
How this whole journey helped you find that issue?
Yeah.
Yeah, so is it because now you have metricized your data, you have time series analysis on top of that, you're only looking at deltas, and you're able to find that what changed, and is this change actually a valid change?
Yeah,
Is that
yeah, that's correct. Because our previous platform, because it would just reproduce the entire table every single day, it was much harder for us to just compare and see the life cycle of that product over time, because you just have a bunch of different outputs that are very, very large. So for us to do this analysis, like, you'd have to like have some really heavy compute to really like drill in here. And this really like wasn't accessible to much of our scientists and our researchers. So it was just really hard. But because we had this way to evolve it, like, we could get really creative and very efficiently inspect those daily diffs of like, okay, on a daily basis, like, what is actually going on.
I see. So you moved full profiling, batch-based analysis for data quality to metric-based, just changed it.
Essentially, yeah.
Yeah, got it.
So for the row-level security, did you have to make any changes on the engines, like Trino and Spark?
No, so we didn't. We have like a very simple approach with the row-level security, where we just give those engines a different URL that like we know that like that specific endpoint is going to map to like a specific tenant. And we got away with this because this is like for internal tenants only, where we don't really need to have those engines mounted with a specific credential or anything like that. But we are going to rework that. We will have these different engines perhaps have like a different type of like credential, and that will kind of be handled in like the REST layer as well.
So on that note, do you support any, other than user ID based row-level access control, do you also support any other predicates?
No, for now, it's like, at least for the first implementation, it's really just on like a tenant or user ID basis.
Okay, thanks.
Upcoming row, I think a row lineage, right? Is it gonna at least partially kind of implement your revision tracking feature, or is this different?
That's a really good question. I don't have the answer to that because I haven't like looked into like what that's gonna look like. But certainly from what I can tell, there are like a lot of really nice features coming up where like I can definitely see how we're gonna like re-implement this. And at least one of the things that I think you had brought up is like leaning into like doing this in a more Iceberg native way and using the spec more can really just make this even more powerful. And that is what we kind of want to do, because we built this product specifically knowing that we had these goals. So we knew exactly how we wanted to design the data model. But what we want to do as a platform is make it easy for like others and kind of have it almost like inbuilt for them. So we are planning on looking into like some of those like features and seeing how we can give a paved path to almost like doing the incremental delivery in the future.
Yeah, thank you for the presentation.
Yep.
Hi, I have a question. So when you write the updates, are you using merge and write, or you reconcile those differences on the client when you read? How does it work in your case?
Are you referring to copy on write and merge on read, or are you?
Yes. Sorry.
Okay. Yeah. We use copy on write to do the merge. Especially because like we do like batch like jobs here, so like we didn't have like a strong push in the beginning to at least do merge on read. But for our client, what we really do is like they're not interacting with the Iceberg table directly. Like we're extracting the data from the Iceberg table and pushing that out as like some type of like Parquet file, for example. So they're just really ingesting Parquet files and like doing whatever they need to do there.
So you don't really have to deal with maintenance of the table in that case.
We can, yeah. I mean, like we can get away without dealing with the maintenance, yeah, because it's not really affecting like our clients and their processes, yeah.
Okay, thank you.
Yeah.
Okay, and I think that concludes this session. Thank you, Rushil, again for the great talk. It was very insightful. And we are turning over the room for the next speaker, so please take any additional conversations into the hallway.
Thank you, everyone.
And please